Hello everyone, welcome to my channel. Today I'm going to introduce another bioinformatics tools for the analysis of tiling-sgRNA CRISPR screen data. Okay, so this tool is developed by me, and you can treat this video as an advertisement of my own computational tools. So, what is the tiling-sgRNA CRISPR screens? Here I will give a brief introduction. So if you have a protein and you want to know which region or which domain of this protein is important for its function, so you can do a tiling screen, like you design all the possible sgRNAs tiling across this protein, and as long as there is an NGG motif, so you design the sgRNA, and then you perform the regular high throughput CRISPR screens, so you can get signals phenotypes at different amino acid for this protein. Usually, the important protein region will cause more severe phenotype compared to other irrelevant regions. Okay, so the reason why this will happen, I will explain in the next slide. Okay, so with these signals, you can get a view of which region of this protein is more important for its function compared to other regions. Okay. Then what's the mechanism underlying these CRISPR tiling screens? Is that if you introduce indel using CRISPR at a certain protein coding region, okay, so you can either introduce indel at outside important region, or you can introduce indel inside the region. Okay, so as long as there's an indel, it will cause either the in-frame indel or frame shift indel. Okay, the in-frame shift indel means there are missing or there are deletion of 3, 6, or 9 nucleotide that will result that in that case the protein can still express, but it will missing some amino acid. Okay, but while for the frame shift, then the protein cannot express normally. Okay, then the whole protein will gone. So in both for the frame shift, both the in-domain indel or out-of-domain will cause the protein loss of its function, while in the protein, in the in-domain indel will cause the protein loss of function even when there is an in-frame indels. Okay, because the important region, if you lose some amino acid, it will cause a dramatic conformational change. Okay, the protein will also lose its function. So the key point is here. If you introduce indel at non-domain or non-important region, it still has some probability to function well as a protein. But if the indel happens in a domain or important region, then the protein has nearly no chance to function well. Okay, then this will cause, if you introduce indels in domain or important regions, it will cause a more severe phenotype, stronger phenotype compared to other non-important regions. Okay. This is a major recently online these CRISPR tiny screens. And if you look at this plot, we have did this large scale analysis on CRISPR screen data, tiny screen data. We found that for the in domain indels, okay, no matter it's in frame or out of frame, then it has no significant difference. While if it's out of domain, the in frame, the high in frame will, the low frame in frame will cause more significant phenotype than the high in frame. Okay, so this further support our argument about this tiny screen analysis. I think the major problem for this kind of screen is that the data is very noisy because you design all the sgRNAs for this protein, but actually not all the sgRNA has equal efficiency, and some of the genes may also have strong off-target effect that cause many different outliers or weak signals which may not be caused by the phenotype by the protein function itself, but it's caused by the sgRNA. Okay, and okay, so you can see here is a signal, CRISPR tiny signal for this SMC2 gene, and at the first glance, we may not be able to find very good patterns. So you can see there are signals all around here, and around here, right? So we need to do some weak signal removal. The basic idea is that the sgRNAs targeting a small region of the protein should be similar to each other, right? Because the protein within a very small short of regions should not be function very differently, okay? In that way, if a signal are very differently from its nearby signals, then it should be an outlier. Then we need to adjust it or remove it. If it's too weak, that means maybe the sgRNA efficiency is low, so we just remove it. Okay, we mark it as gray. So if it's more stronger than other nearby sgRNAs, then it may be because it has a strong target. Okay, then we just adjust it to normal to the equivalent to other surrounding signals. So after this adjustment, we can remove most of the noises, and then we followed of this process. We used called tail greedy unbalanced Haar. Okay, this is a segmentation method based on the unbalanced Haar wavelet. Okay, so this method is very frequently used. The Haar based wavelet method is very widely used for the signaling processing. Okay, so we apply this method to our signals and get its important regions in this signal with this segmentation method. I think this method, the one important advantage of this method is it's not sensitive to the noises within this signals, and it can get important patterns within the noises data. Okay, and through this we can find these three fragments of this protein. Okay, and actually these three regions are corresponding to three important domains: the N-terminal domain, C-terminal domain, and the middle hinge domain. Okay, and these three domains actually are working together to make this protein function well. Okay, So in that way, we can see that our method can are very good at digging out those biological meaningful information from these CRISPR tiny screens, uh, despite the noises called due to the uh, I think it's due to the experimental settings of this uh, tiny screen, tiny CRISPR screens. Okay, so next, I think most people are most concerned, interesting is how can we use these tools for their own data analysis, right? So this tool is called ProTiler. Okay, ProTiler is you can see the Pro is the protein, and tile means tiny across this protein and get the important regions you want. Okay, and you can just install it with pp install, and actually it's you need both Python and R install, because the TGUH the segmentation method used for the detection of the regions is R package called breakfast. So you need to install R, and Python is for other modules, and you need to install the sklearn. So it should be this version, and breakfast you need to install the version 010. So here are how to install these packages. So after you install these packages and breakfast, you may be able to run this program well. So next we will see what's input of this program, and you need to have an input table recording the CRISPR screen data. So this type of data usually have like the genes, a symbol of genes. So, and the sgRNA is targeting this gene, and the corresponding amino acid is target. Okay, usually the amino acid is upstream of the palm, 3 base pair upstream of the palm sequence. Okay, at that loci, and you can map it back to the genome and see what's the amino acid it target. Okay, and also the CRISPR screen data scores. So it can either be the log fold change or the Z scores and Z transform scores. So here this data is performed Z transform on 3 different cell lines. You can see this data. So the symbol, the amino acid, and the scores are the 3 required parameters for this program to run. So the symbol is gene name. So you can either put one gene or list of genes separated by comma. And the amino acid is the cutting loci. Okay, you need to map the sgRNA targeting loci to the protein amino acid loci. And if you have any problems with this mapping, you can ask me. I have a code to map it very quickly. And CRISPR score is the signals. Okay, so you just input the input file, the gene ID, and the same scores. The column, okay, usually is the index of the column. Okay, and the output directory you can either define by yourself, or it will default is a ProTiler output. Okay, if you don't give your own output directory, it will create this directory and put all output files in this directory. Okay, and then here is another 3 parameters. So 2 of them are used to filter out the outlier and weak signals. So if it's more relaxed, that means you need you will contain more signals, but maybe you may include more positive false positives. Okay, and this threshold is to detect the changing point is a segmentation. So if it's more relaxed, that means the region you found may be more wide. So it will not find many so small fragments. So if it's smaller, that means you will find very small regions. That depends on your needs for the cornering of the regions. I think 1.5 is reasonable good for the data set we are testing on. So here is an example of how to run. So the ProTiler, there is a function call. So you just input the table and gene name and the column that recording the CRISPR screen result, either log4 change or the Z-score, and the output is ProTiler output. Okay, so it will output a table for all the regions that are important in this protein. So you can see for this gene, we found these 3 regions and this number of sgRNAs in and the average of the scores. So then we can output a 2-dimension visualization map. Okay, it is called, so this part is the segmentation of the signal, and these are the regions, important regions we found, and we also added the conservation score, the domain annotation, and the secondary structure, the exons, and also the post-modification sites, and the amino acid location. Okay. So these are all the informations you can visualize from this figure. I think it's very informative, and you can have further analysis on 3D if you like. And there's another function for ProTiler is to predict the important regions. But this is just predict it from the protein feature, like this post-modification size, domains, conservation, secondary structure, etc. And you can just put in a list of genes you want to see, and okay, so these are parameters. Usually, the default will be good. It depends on your needs to change some of them to get a better scores. I recommend not to change too many of these parameters, and you can get a list of prediction tables. So whether this amino acid is important for this protein, and we can get the regions for this protein. Okay, so I think this can help you to provide some additional support for your experiment. So if you find this region is important, or if you want to test whether this region is important, you can use this predicting result as a reference. Okay, so usually we cannot rely on 100% on the prediction result because it's always have some false positives, and but for experimental result, usually if you found an important region, and you can go ahead for the experimental test, and then if you find some interesting regions, I think that's good for for interesting biological story. Okay, so that's I think that's kind of end for today's video. And if you have any questions or problems using the software, just let me know, because I'm the author of this software, and I can answer, I think, most of your uh, issues and questions. Okay, so if you like the video, don't forget to like it and smash the subscribe button to stay tuned for my later updates. I will introduce more tools, skills, and scientific research in the bioinformatics field. Okay, and okay, so bye bye. I will see you next time.